Today we are going to do solutions. First of all, there is a topic known as colligative properties. Colligative properties are those properties of a solution which depend on the amount of solute but not the nature of the solute. You all know that a solution is obtained by mixing a solute with a solvent. But there are some properties of solutions which only depends on the amount of solute and not the nature of solute. Suppose you have a volatile liquid and it is placed inside a container. The space just above the liquid will start gathering vapor, and after some time the space above the liquid will be saturated with vapor. Now, the pressure of this vapor, suppose if this liquid is referred to as A, then the pressure of the vapor due to the liquid molecule A is written as PA naught. So PA naught is the vapor pressure due to the liquid molecules which have passed into the vapor state. Now supposing there is another volatile liquid B, and when we take the pure state of B, the vapor pressure is PB naught. So PA naught is the vapor pressure due to A in the vapor state, and PB naught is the vapor pressure due to B in the vapor state. Now the thing is, let's say that there is a non-volatile solute C. Suppose there is a non-volatile solute C and it is mixed with A. So C is a non-volatile solute and it is mixed with A. You will see that now the vapor pressure will come down to some lower value, suppose PA. So there are two laws. The first law states that if you mix A and B, in that case the pressure of the vapor will be equal to PA naught into XA plus PB naught into XB. So if you mix two volatile liquids A and B, then the pressure of the vapor due to both of them will be given as PA naught into XA plus PB naught into XB. This is known as Raoult's first law. The other thing is, if you mix A and C, in that case also the formula will be like this, that PA will be equal to PA naught into XA. So let's understand one thing. When you mix A and B, the vapor pressure will be due to both A as well as B, and we can say like this that we can say like this that PA is PA naught into XA, PB is PB naught into XB, and the total pressure is PA plus PB. So we can say like that. Now suppose when you mix A and C, then the vapor pressure will be only due to A because C is non-volatile. So PA will be PA naught into XA. Now suppose we want to do one calculation like this. PA naught minus PA by PA naught. So it is coming PA naught minus PA naught into XA by PA naught. So that is coming 1 minus XA. So that is coming to XC. XC means mole fraction of C. Now this is known as Raoult's second law. When a non-volatile solute is mixed with a volatile solvent, the relative lowering of vapor pressure is equal to the mole fraction of the solute. Now the Raoult's second law, it tells us that the relative lowering of vapor pressure is equal to the mole fraction of solute. That means the relative lowering of vapor pressure depends only on the mole fraction of solute and not its nature. So the nature of the solute C is not playing any role. The relative lowering of vapor pressure is simply the mole fraction of C. So that is why in our study today, the first colligative property is relative lowering of vapor pressure. This is the first colligative property in our study today. Now, a solution which obeys Raoult's law and it is accompanied by no enthalpy change during formation and no volume change during formation. A solution which obeys Raoult's law, its formation is not accompanied by any enthalpy change or volume change, is called an ideal solution. So in an ideal solution, these three conditions are satisfied. Now it was found that solutions, almost all solutions, they tend to be ideal solutions when they are highly dilute. Now, if a solution does not obey Raoult's law, then it is said to be non-ideal. So a non-ideal solution will not obey Raoult's law, and now we will have a look at some cases where this happens. Have a look at this. So non-ideal solutions are of two types. The first, they show positive deviation from Raoult's law. So have a look at a solution of alcohol and acetone. So suppose you talk about alcohol molecules, you will see that alcohol molecules are hydrogen bonded to each other. Now when we mix alcohol and acetone, what happens is that the acetone molecules, they start disturbing the hydrogen bonding of the alcohol molecules. As a result, the interactions after mixing are poor compared to the interactions before mixing. So in this case, it is found that PA is greater than PA0 into XA and PB is greater than PB0 into XB. So the vapor pressure expected from Raoult's law is not matching, in fact it's greater. So PA is greater than PA0 into XA and PB is greater than PB0 into XB. Now there's another thing, that when you mix these two, then during mixing some energy is absorbed to break the old bonds and some energy is released for formation of new bonds. But I told you that the new bonds are poor compared to the old bonds. So the energy that is absorbed while breaking of the old hydrogen bonds is more than the energy released while formation of new bonds. That means in the overall context, there is a positive enthalpy change. So delta H is greater than 0. Similarly, before the mixture was formed, the interactions were greater, so therefore the molecules were held together more tightly. So there was a compactness, but after mixing, the interactions have become poor. So that's why there is a change in volume. In fact, there is an increase in volume. So in positive deviation, after mixing, PA is greater than PA0 into XA, PB is greater than PB0 into XB, delta H is positive, delta V is positive. Now we know that boiling point is the temperature at which vapor pressure becomes equal to atmospheric pressure. So when we talk about boiling point, it is the temperature at which vapor pressure becomes equal to atmospheric pressure. So in this case, what is happening is that the vapor pressure is becoming more than expected. So the BP becomes lower than expected, and there is a particular concentration of A and B for which we get the least boiling point. So concentration of A and B for least boiling point it gives what we call a minimum boiling azeotrope. So at a certain concentration of A and B, the mixture has least boiling point and it is called a minimum boiling azeotrope. In a minimum boiling azeotrope, the two components boil off at a common temperature which is lower than the individual boiling points. Another thing, since both the components boil off at the same temperature, you cannot separate a minimum boiling point azeotrope by fractional distillation. Ordinarily, in any solution which obeys Raoult's law, you can separate the components by fractional distillation, but minimum boiling azeotrope you cannot separate the components by fractional distillation because they boil off at the same temperature. Next we come to negative deviation from Raoult's law. Suppose you have a mixture of acetone and chloroform. Now, acetone molecules do not have hydrogen bonding among each other. Chloroform molecules also don't have hydrogen bonding with each other, but when they are mixed together, there is a hydrogen bonding like this. So that means the interactions after mixing are greater. So therefore, it is found that PA is less than PA naught into XA and PB is less than PB naught into XB. Another thing is that the compactness of the molecule is disturbed. The compactness is more after mixing, so delta H is less than 0 and delta V is also less than 0. And this is called negative deviation from Raoult's law. Now, in case of negative deviation from Raoult's law, as usual, if we mix the two components at a particular concentration, in that case what will happen? The boiling point will become the highest possible, and at that concentration the mixture is called a maximum boiling azeotrope. So in a maximum boiling azeotrope, the concentration is such that the boiling point is maximum possible and the two components cannot be separated by fractional distillation. So that is the concept of negative deviation from Raoult's law. Okay, now so far we have discussed colligative property number 1, that is Raoult's two laws and also relative lowering of vapor pressure. Second colligative property is elevation in boiling point. Actually, whenever a non-volatile solute is mixed with a volatile solvent, what happens is that the vapor pressure goes down, so the boiling point goes up, and the increase in boiling point is proportional to the molality of the solution, and the constant of proportionality is called ebullioscopic constant or molar elevation constant. Now the thing is that the value of Kb can be found out by help of a formula. M1R Tv naught whole square by delta H vaporization into 1000. So M1 is the molar mass of solvent, Tv naught is the boiling point, R is the gas constant, and delta H vaporization is molar enthalpy of vaporization. So this is the topic, elevation in boiling point. Now we come to colligative property number 3. That is depression in freezing point. So delta Tf is the, when you mix a non-volatile solute with a volatile solvent, then the freezing point of the solvent goes down and the depression in freezing point is proportional to the molality, and the constant Kf is called cryoscopic constant it is also known as molar depression constant. The value of Kf can be calculated by this formula. So m1 is the molar mass of solvent, R is the gas constant, T0 is freezing point, delta HF is molar enthalpy of fusion into 1000. So this is the formula by which we can calculate the value of Kf. Then we come to colligative property number 4, that is osmotic pressure. Suppose there is a solution and there is a solvent and they are separated by a semi-permeable membrane. Suppose there is a solution and a solvent and they are separated by a semi-permeable membrane. So what will happen is the solvent molecules will try to enter the solution through the semi-permeable membrane. So to prevent the passage of solvent molecules into the solution, the pressure that has to be applied on the solution side, this excess pressure is known as osmotic pressure. So osmotic pressure is the excess pressure that you must apply on the solution side to prevent the passage of solvent molecules through a semi-permeable membrane. Now, according to Van't Hoff, he said that the osmotic pressure firstly depends on the concentration of this solution, secondly the gas constant R, and thirdly the Kelvin temperature T, and the relation is osmotic pressure, the symbol is pi, is equal to concentration into R into T. So this is the topic that is known as osmotic pressure. So osmotic pressure is also a colligative property because it only depends on the concentration of the solution and not the nature of the solute. Now, in all the colligative properties we have discussed till now, the first one was relative lowering of vapor pressure. The second one was elevation in boiling point. The third one is depression in freezing point. And the fourth one is osmotic pressure. In all these colligative properties, we have not considered dissociation and association. For example, if you put salt in water, then there is dissociation, so the number of particles gets multiplied by 2 because of dissociation. So according to Van 't Hoff, in every right hand side there should be a multiplier 2 to take into account the dissociation. Similarly, if you consider a solution of acetic acid in benzene, if you consider a solution of acetic acid in benzene, the acetic acid molecule is found to form a dimer like this, and therefore it's an example of association. And according to Van 't Hoff, in the right hand side there should be a multiplier half, because two molecules are forming a dimer to form a single molecule, so it should have a half. So the suggestion given by Van 't Hoff was the right hand side of every colligative property should have a multiplier I. I is called Van 't Hoff factor, and to calculate Van 't Hoff factor, we can just use this concept. Experimental value by theoretical value. So Van 't Hoff factor, we can use this formula, I is equal to experimental value divided by theoretical value. Suppose if there is a single molecule AN and it is dissociating into Na. So if the degree of dissociation is alpha, then we will finally have 1 minus alpha of An and N alpha of A. So the Van 't Hoff factor will be given by I is equal to 1 minus alpha plus N alpha. In the same way, if we write Na is equal to An, so due to association, at equilibrium it will be 1 minus alpha and alpha by N. So I is coming 1 minus alpha plus alpha by N. So this is in case of association and this is in case of dissociation. Now, just like we had colligative properties of solutions, now we will discuss solubility of gas and liquid, that is Henry's law. Now, according to Henry, Suppose if you try to dissolve a gas into a liquid, then there will be two types of pressure in the space above the liquid: the pressure of the gas in the vapor phase and the pressure of the liquid in the vapor phase. So according to Henry's law, the pressure of the gas in the vapor phase is proportional to the mole fraction of the gas in solution. So whenever a gas dissolves in a liquid, the pressure of the gas in the vapor phase is proportional to the mole fraction of the gas in the solution. The constant of proportionality is denoted by Kh, which is known as Henry's law constant. So the constant of proportionality is Kh, which is called Henry's law constant. Now the solubility of a gas in a liquid depends on two factors. One is temperature and one is pressure. First of all, the process of a gas dissolving in a liquid is considered similar to that of condensation, and you know that condensation is a process in which heat is liberated. Condensation is a process in which heat is liberated. So that means the solubility decreases with temperature. So I'll repeat this point again. The solubility of a gas in a liquid depends on two criteria: temperature and pressure. As far as temperature is concerned, the dissolving of a gas in a liquid is considered similar to condensation, in which heat is released, so delta H is less than 0. So that means the solubility decreases with increase in temperature. But as far as pressure is concerned, you can clearly see that there is a direct proportion between the pressure and the solubility. So if you increase the pressure, you will get greater solubility. So this is the two things on which the solubility depends. So temperature, solubility decreases with temperature, and pressure, solubility increases with pressure. Then we come to application of Henry's law. First of all, soft drink bottles, they are carbonated. So to make sure that the carbon dissolves, the soft drink bottle is sealed under high pressure. So once again, whenever we consider a soft drink bottle. You know that soft drinks are beverages which are carbonated, so they contain carbon dioxide. To increase the solubility of carbon dioxide, the bottle is sealed under high pressure. Secondly, suppose there is a deep sea diver. Suppose there is a deep sea diver. Now when the diver goes deep into the ocean, so at this depth the pressure is very high, so the solubility of the gases in the blood of the deep sea diver's body will increase. So excess nitrogen dissolves. So due to the fact that the pressure is very high, so excess nitrogen may dissolve in the blood of the diver. Now when the diver returns to the surface, the excess nitrogen, it comes out and creates a painful condition known as bends. So when the deep sea diver returns to the surface, then there is a painful condition known as bends, because the excess nitrogen, it comes out of the blood. So that is why, to avoid this, the deep sea divers use tanks which contain a certain concentration of helium. So in the tanks, the percentage breakup is something like this: 11.7% is helium, 56.2% is nitrogen, and 32.1% is oxygen. So this is done to avoid the painful condition called bends. Third is those who are mountain climbers, they operate at very high altitudes where the pressure is very low. So there is less oxygen available, and therefore solubility of oxygen in the blood is also very low, and because the concentration is low. So that's why the mountain climbers may suffer from an lack of ability to think clearly, and that is known as anoxia. So this happens because the pressure is very low, and therefore the solubility of oxygen in the blood is also very low. When we were speaking about osmosis, suppose you have two solutions, A and B. Now let us say the concentration of A is greater than the concentration of B. So in that case, Ca is said to be hypertonic and Cb is said to be hypotonic. So if the concentration of A is greater than B, Ca is hypertonic and Cb is hypotonic. Now the fact is that the liquid will flow from lower concentration to higher concentration, so it will go from B to A. Now in another situation, suppose that the concentration of A and B both are same. In that case we say that they are isotonic. So isotonic means there will not be any osmosis at all. Now, suppose we create a method by which sea water, or you may say salty water, is there on one side, and fresh water is there on the other side, separated by semi-permeable membrane. So by using a piston, we apply a pressure which is greater than osmotic pressure. So by means of this particular piston arrangement, we apply a pressure on the salt water which is greater than osmotic pressure. So when we do that, the salt water is basically forced to go in the direction of the fresh water and leaving the salty residue behind. So this particular technique is known as reverse osmosis. So reverse osmosis is the only technique known by which we can take salty water and convert it to fresh water. So it is done by applying a pressure which is greater than the osmotic pressure. Now let's just have a discussion about few examples of osmosis. Suppose you take a raw mango, in salt solution, so it loses water by osmosis and ultimately shrivels to become a pickle. So when raw mango is placed in a salt solution, it loses water by osmosis, and due to that reason it shrivels and becomes a pickle. Second example, what happens is that there is a solution known as normal saline. Normal saline contains 0.9% mass by volume of NaCl. So normal saline has 0.9% mass by volume of NaCl, and it is isotonic with the human blood. So suppose if a person has Suppose, let us say that the human cells are placed in a solution whose concentration is more than 0.9%, then what will happen is water will flow out of the cells, and that's why the cells will shrink. So once again, normal saline is isotonic with the blood. So if the cells have more than 0.9% mass by volume NaCl, in that case water will flow out and the cell will shrink. If the cells have less than 0.9% mass by volume, then water will flow into the cells, and in fact the cells will swell. So this is regarding the functioning of normal saline. Then third example is wilted flowers. They get revived when they are placed in fresh water. So limp carrot is revived in fresh water. So these are the various examples of osmosis. That brings us to an end of this particular session of the chapter Solutions.